You may remember at the beginning of the course, I said that a course on time often is the kind of course where you leave knowing less than when you came in. And my students always kind of laugh about that. And every once in a while, at the end of the semester, they'll say, Dr. Robson, you're right. I really have no clue what just happened. And usually they start to think that right about now. So think about it. We've gone through some interesting religious ideas. We've gone through Aristotelian science. We've gotten into Newtonian science that really explains the world the way we see it around. The problem is Newton is probably wrong. In a way, Newton works really, really well. And the kind of science that predicts and controls the future works very, very well on our everyday level. But if you pull the focus out to a big cosmic level, Newton doesn't quite work. And if you push the focus in to the subatomic level, it gets even weirder. What I hope, though, is that the ideas that we've developed so far will be really good and will serve us well when we're trying to figure out this craziness of relativity, this craziness of quantum, this craziness of what we call the modern world. Here's one more little quote for you. And it doesn't come from Einstein. It doesn't come from a poet. It comes actually from Karl Marx. And you don't think of Karl Marx as a poet, and most of the stuff he has written is a pretty hard slog if you've tried to read it, as I've tried to make myself over the years. But he has a wonderful line about halfway through the Communist Manifesto when he's talking about the new world, the modern world that he sees coming. And in this, I think he's very smart. And he says, in the modern world, all that is sacred is profaned. All that is solid melts into air. And what he means by that is that everything we thought we understood is going to dissolve away. Whenever we think we get it, we're going to realize that we don't really get it. And that, brothers and sisters, is the modern world, the world of Einstein, the world of quantum, the world of existentialism, the world of absurdity. The first thing to try to understand when we're thinking about Einstein and the encroaching idea of modernity, or what we might call the Einsteinian paradigm. So if we move from the Aristotelian to the Newtonian, now we're moving from the Newtonian to the Einsteinian paradigm. The first thing to think about is Einstein's understanding of time. Here's a caveat. I don't really understand this stuff. If you had ever seen my calculus grades, you would agree that I don't really understand this stuff. I'm completely betting here, though, that there are people out there like me who did not do that well in calculus, and so were not really able to do the mathematics of theoretical physics. In the hopes that that's the case, I'd like to introduce you to Einstein's ideas about relativity in the way I think about them, with the hopes that maybe it will help you think about them a little bit too. If not, we can all stop, take a MOOC on calculus, and come back to this spot later on. But here goes. Early in the 20th century, Einstein really came out of the blue scientifically and wrote a paper in which he described the problem of special relativity. Basically, it says this: time is not linear in that it doesn't go in one straight line, and time is not absolute. So right away, it starts to undercut everything we know about science, because all the things we know about Newtonian science are predicated on this idea of time moving in one line in absolute lockstep, 1 second equals every other second. So there are two kinds of relativity that Einstein was interested in. This first one is special relativity. What I'm going to describe to you is not exact, but again, it's the way I think about it, and maybe it'll work for you. Good. So imagine that you've got this great super ball, a bouncy ball that is really, really good. And if you drop that ball, it goes down, say 1 meter, and it doesn't lose any energy. It comes all the way back up 1 meter. So every time you drop it, it goes down a meter, comes back a meter in, say, 1 second. It goes down a second, up a meter, or up a second. So 2 seconds, 2 meters. It doesn't lose any energy. Remember, this is just a thought experiment, so we can say whatever it is. So you've got this really cool bouncy ball. And every time you drop it, it goes down a meter, comes up a meter. It takes 2 seconds. So in other words, in 2 seconds, it goes 2 meters. Easy enough, right? Good. So you're bouncing, 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 bouncing. We understand that. What happens, though, if you bounce that same ball on a train as the train is moving? Well, the answer, of course, is nothing happens. When you bounce a ball on the train, it drops straight down and comes right back up. It's just like it, on the ground or in a plane. It doesn't matter. He calls that the frame of reference. So within the frame of reference of the train, the ball is going down a meter and up a meter in 2 seconds. Easy enough. What happens, though, if the train were all glass and there was somebody else watching you bounce that ball? In that case, the ball would start in one place, and as it's dropping, the train is moving forward. So the ball is dropping, but it's also going forward and then going back up at another angle. So to you, in that period, the ball has moved 2 meters. But to someone in a different frame of reference, it's moved more than 2 meters. So special relativity says, and again, that's not precisely right, but it helps me in my head, that basically time goes faster or slower depending on A, your speed, and B, your frame of reference. So the great example of this, of course, happened in the 1970s with atomic clocks and jet airplanes. And some really smart scientists took 2 atomic clocks that were absolutely precisely set at the same time. One stayed on the ground, went on an airplane and went really fast around the world. And when it came back, you guessed it, the clocks were no longer the same, because the one that was moving faster had time moving slower than the one on the ground. The great idea that people always talk about would be absolute twins going into space. If one goes first, or say one stays on the ground and the other twin goes up, the twin that goes up into space and is moving really fast comes back slightly younger than the one who stayed on the ground. Strange, huh? That's special relativity.